Hello Bobcats. Today I'd like to talk about orbital diagrams and electron configurations. So the first thing we need to address is something called the Aufbau Principle. Which states that electrons enter orbitals of lowest energy first. So here I have a set of orbitals here in which we have energy level 1, energy level 2, energy level 3, and energy level 4. And we notice that energy level 1, in energy level 1 we have one sublevel, that's an S sublevel, and that S has one orbital. Then we have to move up to the next energy level. Now energy level 2 will have two sublevels, an S and a P sublevel. The S will have one orbital and the P will have three orbitals. And I'm just drawing lines to represent the orbitals. And if it helps, you can think of this as the 1s, and then this would be the px, the py, and the pz orbitals. And we notice here also that the p orbitals are slightly higher in energy than the s orbitals. So as we put in electrons, they will go into the 1s, then the 2s, and then they'll go into 2p, and then when the 2p is filled, they will go into the 3s, and then the 3p. And we also notice here that there's a difference between the 3p and 3d, but in between the 4s fits in here. So actually, as far as energy goes, the 4s sits a little bit lower than the 3d, and then we go to 4p, and it continues that way on up the chain, or the energy levels, I should say. So if I were to look at a periodic table, and let me see if I can put one to the side over here so that we can see what's going on. We'll just start here. And we notice that if I use the blocks, each square to represent an electron, or we can say that hydrogen has one electron, that first electron, or that one electron of hydrogen, will fit right in first here. Now, Paulie principle states that, or the Paulie exclusion principle states that they can have only two electrons in each orbital, and that those electrons must have opposite spins. So I'm showing an electron here with an up arrow. I know it's only a half arrow, but it's still an up arrow. And then the next arrow, the electron that would go into this space would be a down arrow, or an electron of the opposite spin. So this would represent hydrogen. So hydrogen is a 1s with one electron in it. Energy level 1, sublevel s with an electron in its orbital. Then if we look at the next element would be helium, and helium has two electrons. So helium would have the next electron, and so this would represent helium. And helium would be have a 1s with two electrons in it. Now that's filled, so you have to go to the next energy level, and the first sublevel in that energy level is the S. And so if we go back, we're done here, we finished this, so we have to start over with the next energy level, and I'll write those in here. We got 1, 2, 3, 4, 5, 6, 7. So now I'm on the second energy level, and the next element has 3 electrons in it. So lithium has 1, 2, and then 3 electrons. So lithium is a 1s with 2 electrons, and then a 2s with 1 electron. And then beryllium would be the next one with 4 electrons, so I put in a 4th electron. You notice that these are both in the s orbitals, and if you'll notice, hydrogen, lithium, and beryllium are in these two columns, and so we call this column the S block. So we have an S block column here. Now, the next electron would have to go into the second energy level, but the p sublevel in the px orbital. And if we look at our periodic table, our next element has its boron with 5 electrons. So we have 1, 2, 3, 4, 5 electrons. And that would be, so my boron has a 1s with 2 electrons, a 2s with 2 electrons, and then a 2p with 1 electron. Now, if I wanted to show this with electron configuration, I can show you that boron, and I'll use a different colored pen here so you can see, and I'll write this down. We're looking at electron configuration. In which we see that if I'm looking at the element boron in this case, and boron has 5 electrons, if we did this, we have a 1s with 2 electrons, so I'd say 1, that's energy level 1, sublevel s with 2 electrons. And then it has energy level 2, sublevel s with 2 electrons, so that'd be a 2s with 2 electrons. And then we also have energy level 2, but we have p sublevel, so that's energy level 2, p with 1 electron in it. So this is the electron configuration for boron. If you'll notice, it's 2, 4, 5 electrons, and the electron configuration shows you what energy level and sublevel those electrons are occurring. Now, if we continue with this, Hund's rule states that if you have orbitals that are of the same energy, such as these p orbitals, then you put electrons in each orbital before you double the electrons up. So if the next element we look at is carbon, and carbon has 6 electrons, so I go over here and I say 2, 4, 5, 6 electrons. Remember, I have to put an electron in each orbital before I double up. That's Hund's rule. If I wrote the electron configuration for that, I would say this is carbon, and it would be 1s with 2 electrons, so that's a 1s2, 2s with 2 electrons, so that's a 2s2, and then a 2p with 2 electrons, a 2p with 2 electrons. So this is the electron configuration for carbon. I continue, and so if I look at this, the next element is nitrogen, and it's got 7 electrons as a neutral element. Really, the 7 stands for 7 protons, but as a neutral element, it's got also 7 electrons. So I look at this and I put, that's 2, 4, 5, 6, 7. So that's the representation for nitrogen. And to draw the electron configuration for nitrogen, I would say that nitrogen has a 1s2, 2s2, and now it's got 2p with 1, 2, 3 electrons. So that's a 2p with 3 electrons. And I'm going to continue this for a couple more. We notice here, next one would be oxygen with 8 electrons. And if you notice, these electrons, 5, 6, 7, and 8, that's 5, 6, 7, and the next one would be 8, so oxygen would have 1 down. These electrons are in the p orbitals, and so if you look at this, we would call this, from here to here, the p block, because there's 1, 2, 3, 4, 5, 6 elements with which would represent 6 electrons, and we can fit 2, 4, 6 electrons into the p sublevel. As I continue though, we got to write the electron configuration for this. So oxygen would have an electron configuration of 1s2, 2s2, 2p4. Now you can think of this Aufbau diagram here that I'm showing here is also an extended or expanded orbital diagram, because I'm showing the energy, how the energy increases. I'll show you an easier way to draw orbital diagrams later, but an orbital diagram gives more information than electron configuration, because electron configuration just tells you how many electrons are in that energy level and in those sublevels, whereas the orbital diagram will tell you what orbitals those electrons are in, which is important because now we see that there's two empty spaces here, and so I can either make two bonds with oxygen or gain two extra electrons to have a -2 charge for oxygen. So if I continue with this, you'll notice that we have, after oxygen, we have fluorine with 9 electrons. So that's 2, 4, 6, 7, 8, 9 electrons. So fluorine would be, let's go down here, fluorine would be 1s2, 2s2, 2p5. And then if we continue this, the last one on this second energy level is neon with 10 electrons. So I put the 10th electron in there, and as we write this down here, we would have neon 1s2, 2s2, 2p6. Again, 1s with 2 electrons, 2s with 2 electrons, and 2p with 2, 4, 6 electrons. Now we have a completely filled second energy level. So the next electron will have to go into the third energy level, and the first energy sublevel with lowest energy would be the S sublevel. And so to correlate that with my periodic table, we notice we're done here. This is the same energy, so I start back over, and I start with sodium on the third energy level with 11 electrons. So here we go again. I've got 2, 4, 6, 8, 10. This would be the 11th electron, and it goes in the S block first, or in the S orbital first. Now, let's talk about how I can make it a little bit easier. This is called a complete electron configuration, but I can do what's called a noble gas notation of the electron configuration, because we notice here that this is a completely filled, two completely filled energy levels. And so if I were to write sodium's, I'm going to do it in a different, well, I'll do sodium's. If I do sodium's electron configuration, we have 1s2, 2s2, 2p6, and then we ended up with a 3s with 1 electron, so that's 3s1. But we notice that this right here is already represented as a completely filled energy levels, the first energy level and the second energy level. So instead of having to write all of that over, we can use neon that has the 10 electrons with a completely filled energy level to represent that. So we would just say, in brackets, we would say neon, that represents these 2, 4, plus 6, 10 electrons here, neon, and then I would just write 3s1, so that I don't have to write all of that. I can write neon 3s1, and now I'm just working with that third energy level. And you continue all the way up. If I were to continue adding electrons, I would add to the S, and then I would go the P, and then the next one after 3P is not 3D. The next lower energy is the 4S. So I'm not going to continue writing electron configurations, but if you'll notice, the way this would go is that I would enter an electron here that would represent, let's that's 12 electrons that would represent magnesium. And then I would have 13, that would be aluminum. 14 would be the number of electrons for silicon. Then we'd have phosphorus. So if you think about it, this is 1, 2, 3 electrons in the P. If I count, remember this is the third energy level, so that's 1, 2, 3, that's P. And if I want to check, that's 15 total electrons. I can look 2, 4, 6, 8, 10, 12, 13, 14, 15. Now the next one would be sulfur. So I would put the next electron in here for sulfur. Then we would have chlorine right here, chlorine, and then I would fill that energy level with argon. That's 18 total electrons. So if I look at it, 2, 4, 6, 8, 10, 12, 14, 16, 18. Now the next electron that would go in doesn't go into 3D. It would go in something slightly lower in energy, which is the 4s. And if you look at your periodic table, once we're done with argon, number 18, the next one is number 19, which is potassium, but it's on the 4th energy level in the S block. So that would be 1 electron, so that'd be 4s. So if I look at this, and I'm just going to write the electron configuration for potassium. So for potassium, remember I already have a filled energy level here at 18. So when I'm looking at potassium, I go up and all the way to the end. I can use argon to represent all the other filled energy levels. So I would write in argon 4s1. So that would be potassium. The next one after potassium would be calcium, which has got 20 electrons. So now we have calcium that has, I'll put in the next electron. So again, I would go back down here and write calcium, and I would use argon to represent all of those other 3 energy levels that are full. And remember, calcium 4, and it's in the S block, so that's 4, S1, S2. 4, S2 right here. So I'd write 4, S2. Now, the next element, we don't jump up to the 4P. What we notice here is that the D is slightly lower than 4P and a little bit higher than 4S. So the 3D is the next one that goes in. So if I'm looking at scandium right here, number 21, that's 21 electrons, you'll notice that it is in what we call the D block. Now remember, D has 5 orbitals which can fit 10 electrons. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so this is the D, but remember, we start on a lower energy level for D, so that's actually 3D. And I put that 1 electron right here into 3D. And if I were to write the electron configuration for that, I would write scandium, and then it would be argon, which represents the first 18 electrons with filled energy levels, 4, S2, 3, D1. Now, it doesn't matter if I put it as 3D1, 4S2. It doesn't matter what order as long as you get the energy level and sublevel correct. So I could, and you will see this in a lot of textbooks, written as argon 3D1, 4S2. So either way is correct for scandium. So that's how the electron configurations work with the Aufbau diagram and filling in orbitals in order of energy, the lowest energy to highest energy. So we've followed the Aufbau principle. We also have followed what we call Paulie exclusion principle. So the Paulie exclusion principle states that electrons I'm sorry, it's not electrons. States that an orbital will only allow 2 electrons of opposite spin. Okay, so if you notice, each one of these orbitals has a spin up or spin down, or you might think of it as a clockwise spin and a counterclockwise spin. And then the last thing that we learned in doing this was Hund's rule. And Hund's rule states that don't know if I left enough space, but Hund's rule states that electrons will go into orbitals of same energy before doubling up. Doubling up. In other words, if I were to continue to put electrons in this d orbitals, I would have to put 1, 2, 3, 4, 5 before I go back and put the second one in. Now that kind of makes sense, because remember, electrons are negative and they repel each other, so they really would rather not be in the same orbital. So if you have orbitals of the same energy, you put them in individual orbitals before you double up. It's kind of like if I had siblings. And let's say I have, and let me just give you an example here for the Hund's rule. This is an example. I have 3 p orbitals. Well, or think of it as 3 rooms. If I have 3 siblings and they all fight all the time, I wouldn't put 2 siblings in one room and another in a second room and then leave one room open. That would not make sense. I would put all 3 siblings in a different room to keep them from fighting each other before I would have to put another sibling in. So you would put electrons in 3 separate orbitals before you double up. So this is an example of Hund's rule. So here we look at Aufbau Principle, which electrons enter orbitals at lowest energy first. Paulie exclusion principle, stating that an orbital or orbitals will only allow 2 electrons of opposite spin, no more. Then Hund's rule states that electrons will go into orbitals of same energy before doubling up. And so we see here a Aufbau diagram, orbital diagram. If you want to know what this is, right here. This right here is an Aufbau orbital diagram. Getting kind of messy, but I'll try to clean this up later. Diagram. So here we see an Aufbau orbital diagram to show that they go in first lower energies, and then I relate that Aufbau orbital diagram to the electron configurations here, which show the energy level, the sublevel, and how many electrons are in that sublevel. Over here I've shown how we take a complete electron configuration and use a noble gas notation of the electron configuration, showing that that noble gas with 10 electrons represents these filled energy levels. That takes 10 electrons. And then I show how we first go into 4s before we go to a 3d. And that is orbital diagrams and electron configurations first lesson. I'll do another lesson, part 2, in just a minute. Thank you.